Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Bridging Between Algebra and Calculus series and concerns inverse functions and graphs. This guide introduces the concept of the inverse of a function and its relationship to its graph, and multiplication being undone by division. In mathematics there is a specific word to describe the idea of undoing. It is inverse. So subtraction is the inverse of addition, just as addition is the inverse of subtraction. The idea of an inverse can be extended to functions, as the more complicated mathematical expressions which make a function are created from combinations of basic operations. However, do other functions such as sine, cosine, exponential and logarithm have inverses? This guide aims to show you how to determine whether a function has an inverse. Before you continue, you should make sure you are familiar with the notation and concepts associated with functions. The study guides, functions, and using functions can help you with this. The inverse of a function. If you think about a function as a machine which changes an input into a unique output, then the inverse of this function would also be a machine which changes the output back into the input. Importantly, the inverse of a function is also a function. The idea of a function can be expressed mathematically as the function f has an input of x and output f of x. The inverse of this function, if it exists, is written f minus 1 of x. It is very important that you realise that the superscript minus 1 in f minus 1 of x indicates the inverse of a function and not an index. It is common to confuse the inverse of a function with the reciprocal function, and you should always take note of the context in which the minus 1 appears. If the piece of mathematics you are looking at concerns the laws of indices in some way, the minus 1 probably represents the reciprocal. On the other hand, if you are looking at functions, then the minus 1 probably means inverse. Not all functions have inverses. Only functions which are bijections, those which are both injections, 1 to 1, and surjections, onto, have an inverse. These functions can be identified as functions where each output can be paired with only one input. You can represent the idea of a function and its inverse pictorially. The top diagram shows a function f with an input of x and with an output f of x. Start with some input x. This is inputted into the function f, represented by this box. The output from the box is f of x. The lower diagram shows that if the output of the function f acts as the input to its inverse of f minus 1, then the resulting output is x. If the input is f of x into the inverse function f minus 1, then the output is x. Example: find the inverse, if it exists, of f of x equals 2x minus 3. First of all, you have to check if the function has an inverse, i.e., is it a bijection? In order to do this, you have to check if each output is paired with only one input value. Indeed, for every input x there is a unique output, so f is a bijection and f minus 1 exists. To find the formula of f minus 1, you have to work out what operations would undo the mathematics involved in f of x equals 2x minus 3. It is crucial to get the operations in the right order. A simple flowchart method could be a useful tool for this process. See study guide, Rearranging Equations. You create the function f of x equals 2x minus 3 by first multiplying the input by 2 and then subtracting 3. The flowchart for this might look like this. For f, start with x in a box, multiply by 2 to get 2x, and then subtract 3 to get 2x minus 3. The inverse of this process is taking an input and adding 3 and then dividing by 2. The flowchart procedure for this looks like, for f minus 1, start with x in a box, add 3 to get x plus 3, and then divide by 2 to get x plus 3 divided by 2. So the formula of the inverse function is f minus 1 of x equals x plus 3 all divided by 2. This process for finding an inverse function is not always straightforward. Sometimes you may encounter difficulties in showing that a function is a bijection. Learning the language and definitions of functions can help you with this. Also, finding the function formula f of x could prove to be a challenging process. Becoming familiar with the flowchart method can help you overcome this. It is important for you to know when a function does not have an inverse. Example: find the inverse of the function f of x equals x squared when x is a real number if it exists. Firstly, you have to check if the function is a bijection. The squares of numbers with opposite signs give the same result. For example, minus 2 squared and 2 squared both equal 4. This means that each output value is paired with two different input values. Specifically, for f of x equals 4, x can either be plus or minus 2. Therefore, f of x equals x squared is not an injection, therefore not a bijection, and thus does not have an inverse. Connection between functions, inverses and graphs. You can think of a coordinate on a graph as defined as x f of x. As you have seen, the inverse of a function swaps the roles of input and output in the original function. As a result, if the point x f of x belongs to the graph of a function, then the point f of x, x will belong to the graph of its inverse. There is a nice way of thinking of this by considering the graphs of a function and its inverse. It is always the case that the point f of x, x is the reflection of the point x f of x in the line y equals x. A direct result of this is that the graph of f minus 1 of x is obtained by reflecting the graph of f of x in the line y equals x. Example: sketch the graphs of f of x equals x cubed and its inverse. In the figure to the right, you can see the graphs of the function f of x equals x cubed, which is the dotted curve, and its inverse f minus 1 of x equals x to the power a third, the solid curve. It is clear that they are reflections of each other in the diagonal y equals x, the dashed line. Example: find the inverse of the function f of x equals e to the x and sketch its graph. The function f of x equals e to the x is a bijection, and so it has an inverse. The laws of logarithms tell you that if f of x equals e to the power x, then the natural logarithm of f of x equals x, and you can write f minus 1 of x equals the natural logarithm of x. So, natural logarithm of x undoes e to the x, and the inverse of f of x equals e to the power x is the function f minus 1 of x equals natural logarithm of x. The graphs of these functions are shown to the right. You can see that f of x equals e to the power x, the dotted line, and f minus 1 of x equals natural logarithm of x, the solid line, are reflections of each other in the line y equals x, the dashed line. You can see that two basic functions, the exponential and logarithmic functions, are inverses of each other. This is discussed in more detail in the study guides Basics of Logarithms and Exponential Functions. The trigonometric functions also have inverses which are useful to know. The inverse of sine x is sine minus 1 of x, often written as arc sine of x. Similarly, the inverse of cos x is cos minus 1 of x, often written as arc cos x. Further guidance and information. If you have any further questions about functions or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a learning enhancement tutor in the Dean of Students office. Telephone 01603 592 761. Email dos.help@uea.ac.uk or visit our website www.uea.ac.uk/dos/let. There are further resources on many other aspects of numeracy, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills.